Hello, I'm Charlie Lin, and I'd like to present my project on vesicle dynamics in large amplitude oscillatory extension. To begin this presentation, I'd like to acknowledge the other authors on this project, starting with Dr. Shiyan Wang and my advisor, Professor Vivek Narsimahn. I'd additionally like to acknowledge my collaborators from the University of Illinois, Dinesh Kumar, Channing Ritcher, and Professor Charles Schroeder, who have worked on the experimental side of this project. In this presentation, I'll begin by describing the vesicle and LAOE system, and then going through the methods we've used in this project. Then we'll be going through the results, starting with the experimental and numerical results comparison, then looking at the dynamical regimes currently predicted by the numerical results, and finally the stress response for a dilute vesicle suspension in LAOE. And then we'll wrap things up with the project conclusions. So firstly, a vesicle is simply a droplet enclosed by a lipid membrane, and a simple diagram of such can be seen on the right. Vesicles are important in a whole host of biological functions, such as storage and transfer of nutrients or cell signaling. On the right, we can actually see an image of a vesicle fusing with a plasma membrane in order to secrete the contents within. Now, vesicles are additionally used on many lab-on-a-chip type applications, either as cell mimics, artificial cells, or even in drug delivery. On the right, we can actually see a vesicle being used to capture or contain a live cell. Additionally, vesicles are very commonly used as a model system because they actually mimic the dynamics of anuclear cells, such as red blood cells, quite well. Now, vesicle dynamics and steady flows have been very well studied, in particular looking at steady shear flows and steady extensional flows. In practice, however, such as looking at flow through a microfluidic device, the flow that a vesicle experiences are not always going to be steady, and it's quite important to actually look at vesicle dynamics in time-dependent flows. In particular, a previous study by Canceller and others has shown that even with a simple time-dependent flow in which they had a step extension of flow in which the flow was turned on or off or reversed in direction suddenly, that they already saw a wealth of new dynamics, such as this transient wrinkling effect that occurs when the vesicle is under sudden compression, or even this budding effect at higher flow rates. Rather than looking at extensional flows, in this study we want to see how vesicle dynamics are affected by an oscillatory flow in particular. Additionally, it's important to know that single vesicle dynamics are quite important for interpreting their bulk rheology. It is now well known that vesicles in shear flows undergo this tumbling to tank treading transition, and during that transition, they actually see a minimum in viscosity at the transition point. Now, similar dynamics can occur when we're looking at compression and extension of vesicles. And we want to see how that said extension and compression of vesicles can affect their bulk suspension rheology. Now, just to define the project objective, we want to look at how vesicle dynamics are affected by LAOE and what rheological information we can gain. We have chosen to use LAOE in particular because this isolates the effect of vesicle strain on the rheology in comparison to looking at a shear flow in which you have a rotational component. Additionally, by using large amplitudes, we can probe the nonlinear stress response. Now here I'm just giving an overview of the project in general. We're looking at time-dependent vesicle dynamics and the rheology of the compression and extension of vesicles. We want to examine the vesicle dynamics in an oscillatory extensional flow, and we'll be focusing on quasi-spherical vesicles and large amplitude strain rates. We are approaching the project with two methods: an experimental method in which we're using microfluidic flow control, and track a single vesicle using optical microscopy. We're also doing additional direct numerical simulations using the boundary element method. Now I'd like to go through the methods used in this project. To begin with, I'd like to define the external flow field, defined as a velocity gradient here, which we have essentially these sinusoidal terms and flow frequency terms. So essentially what we have is this planar XY flow that changes directions based on the flow frequency term. For the experimental setup, our collaborators create DOPC vesicles formed through the common electroformation process, and then implement flow control and trapping using their Stokes trap setup, in which they essentially have a PDMS cross-slot device with 4 fluid reservoirs in order to create a stagnation point in which you can track per vesicle and then image the vesicle using optical microscopy. Now, to model the membrane or vesicle system in particular, we have chosen to use the steady Stokes equations. And this is simply due to the fact that at the length scales we're looking at, there's very low Reynolds number. And additionally, at the flow frequency we'll be looking at, the Wormsley number is also quite small, so we don't have to take into account time dependence. To model the membrane itself, we've chosen to use the Helfrich model, in which we have this first term on the right-hand side, energy from the curvature of the membrane, and the second surface tension term actually as a constraint to implement this membrane compressibility constraint. Now I'd like to go through some of the non-dimensional parameters of interest in this project, beginning with the reduced volume, which is essentially a measure of the asphericity of the vesicle. On the right, we can see that a reduced volume of 1 corresponds to a perfect sphere, and lower reduced volumes become increasingly deflated, in which you can have more bending occur. Next, we have the viscosity ratio, which is simply a ratio between the inner fluid viscosity and the outer fluid viscosity. Then we have the Kaplan number, which compares the viscous stresses to the bending stresses, and essentially is a measure of how strong the flow is in comparison to the bending resistance. And finally, we have the Deborah number, which is simply the flow frequency divided by the bending time scale, such that we have a non-dimensional flow frequency. For some additional parameters used in this presentation, we'll be looking at the time-dependent Kaplan number, which is simply the Kaplan number multiplied by the sinusoidal term seen in the velocity gradient previously. So this is essentially an instantaneous strain rate measure. Next, we have a deformation parameter, which is the difference between the lengths of the vesicle in the x and the y directions divided by their sum. And this parameter gives an idea of how deformed the vesicle is and in which direction the vesicle is oriented. Now we can go through the numerical or the results in the experimental numerical comparison. To begin with, I'd like to draw attention to this phase space diagram in Kaplan number, Deborah number space, showing the simulations and experiments. So we can see that for the current experiments we have in this presentation, that the experiments are working at quite higher Kaplan numbers in the simulations due to some experimental difficulties. So in this next section, we'll actually be looking in particular in this compare section between the simulation and experiments. So here I'm showing on the left an experimental video of a vesicle deforming an LAOE, and on the right, for the same parameters, a simulation of said vesicle deforming. And we can see that we get very similar shapes between the experiments and simulations. In both videos, we see the transient wrinkling effect. To compare these more quantitatively, on this slide, I'm plotting the deformation parameter in comparison to time for 3 sets of parameters, comparing the experimental results in black, the simulations in purple, and the strain rate in this dotted blue line. We can see essentially a very good agreement between the maximum deformations of the experiments and simulations, and also a decent agreement for the transitions in between these maximally deformed states. Additionally, we see in all 3 of these parameter sets that the vesicle essentially deforms very symmetrically in that they reach the same magnitude deformation parameter in both directions. And this is going to be quite important in the next couple of slides. We can now look at the dynamical regimes currently predicted by the simulations. So to begin with, we have the symmetrical regime in which the vesicle deforms symmetrically in both the x and the y directions, and this is exactly the same dynamic as seen in the previous slide. But as we decrease the Kaplan number, keeping the Deborah number constant, we can actually go into the reorienting regime in which the vesicle deforms unequally in the x and the y directions. This is quite different from what is actually seen in the droplet dynamic case, in which a droplet for the first couple of cycles can deform this unequally, but in the limit cycle, behavior will actually deform symmetrically. This is actually what is seen for vesicles in a limit cycle behavior. And if we decrease the Kaplan number even further, we'll actually see that the vesicle will stay in one orientation and just pulsate along a single axis. Now, if we plot the deformation parameter in comparison to the Kaplan number x, what we can see is that we can use the deformation parameter to actually differentiate between the pulsating, reorienting, and symmetrical regimes. What we just have to do is look at the minimum and maximum values of the deformation parameter, and should they be of the same magnitude, we're in the symmetrical regime. Should they be different magnitude and different in sign, we're looking at the reorienting regime. And should they be of the same sign, we're looking at the pulsating regime. And doing such, we can actually construct a phase diagram for the regimes. And that is done here in the Kaplan number, Deborah number space for a reduced volume of 0.8 and viscosity ratio of 1 on the left, and a reduced volume of 0.9 and viscosity ratio of 1 on the right. And we'll see that we have very linear phase boundaries, and the same trend is seen for other viscosity ratios. This suggests for the phase boundaries are a simple relation between the flow strength and the flow frequency. Additionally, you can see that the lines that we have in these graphs are actually from our perturbation theory analysis with a 5% error. Now we can look at the stress response of a dilute vesicle suspension. So we can actually get the extra stress for our dilute suspension just by calculating the particle coefficient of stress slit multiplied by the number of particles or vesicles in this case. So you can calculate the particle coefficient of stress slit by integrating this traction term and integrating this velocity term, and then non-dimensionalizing by vesicle volume and strain rate. Then we can essentially get these normal stress difference terms, which have the first normal stress difference being the XX minus the YY contributions, and the second normal stress being the YY minus ZZ contributions. So then we can plot the normal stress differences versus time as seen here for the three indicative parameter sets for the three regimes, and we can see the stress over 2 cycles. So a purely linear stress to strain rate relation will actually produce sinusoidal first normal stress curves, and we can see very clearly that for all three regimes here, we're actually getting a nonlinear response in all the regimes. To actually quantitatively interpret these results, we can actually do a Fourier transform analysis of this stress response, and that is done here in which we're doing the Fourier decomposition of the three same parameter sets. So we can see that there's a higher order dependence on strain and strain rate observed in all three regimes, and very interestingly, between the reorienting and symmetrical regimes, we see that the symmetrical regime actually loses all of the even modes for the first normal stress difference, and this is consistent with the phase boundary mentioned previously between the symmetrical and reorienting regimes. Now, it is important to note that all modes are possible to be excited in this Fourier decomposition analysis in oscillatory extensional flow. This is in contrast to what is seen in oscillatory shear flow, in which only these odd modes are seen. It is very likely that we only see the odd modes in the symmetrical regime simply due to the fact that the vesicle actually deforms symmetrically in that regime. And now we can wrap things up with the conclusions. So in this project, we've been looking at the experimental and computational study of quasi-spherical vesicle dynamics in large amplitude oscillatory extension. We've been compared between experiments and simulations, specifically in the symmetrical regime, and there have been very good agreement between the experiments and the simulations currently. We have additionally predicted 2 other regimes in the pulsating and reorienting regimes that are essentially based on the ratio between the flow frequency and flow strength, and we're currently working on getting some experimental results in the pulsating and reorienting regimes. And finally, we see that the microscopic anisotropy in the pulsating and reorienting regimes can actually lead to very interesting bulk rheology as seen in the Fourier decompositions. That concludes my presentation, and thank you all for your attention.